Yes. What we'll do is today study the design of multiple input change, so hazard-free circuits. We have already studied single input change circuits, and then we found that you basically look for adjoining ones in sum of product form. You look for adjoining ones to get a static one hazard. You look at adjoining ones, and then you include a redundancy by a additional product term which covers these adjoining ones that are not part of the same covering cube. So you know that every covering cube that we have in a Carnot map will correspond to if in a two-level circuit, it will correspond to the AND level in the first gate, and combination of them are fed to the second level OR gate. So every term here, every cube here is an AND gate. And we saw that basically if we have two ones in SiC which are not part of the same cube, then there may be a potential hazard, because that for some input combination for that particular variable which is changing the value, because if it's adjacent means one variable is flipping the values. So for that variable there is a plus a bar kind of situation for some combination of other Wx or other values, which you want to avoid because of the delays they may lead to glitches. We come up with a more general scenario here. So in the SiC, we assume that only one of the bit will transition. Okay, there will be a monotonic transition of one of the bits. So it will be 0 to 1 or 1 to 0, but not 0, 1, 0, this kind of thing. And the output is, there are two kind of possibilities. One is a static possibility, whether the output is static or always 1 even in spite of this change, or always 0. And then we call a static 1 and static 0 hazard, or there may be a dynamic hazard. So the output moves from 0 to 1 or 1 to 0, and there may be a non-monotonic change in the output, which we call as a dynamic hazard. And both of these we find that just it's very easy to remove them. You add an additional covering cube which covers this adjoint non-common one, and so that introduces an additional AND gate, and that will force the output OR to be 1 even under glitches. We have had the glitches. All right. So what we study now is a multi-input change scenario. So you suppose, for example, here look at this Carnot map. We have 4 variables x, y, z, and w, x, y, z, and there may multiple of these variables may change. So maybe initially the values of the variable is, let's say, 0, 0, 0, 0, and from them, which we call as the source value M1, in our terminology we'll call it as M1, the initial main term at which the input was there, and then you have a final main term M2, which is, let's say, 1, 1, 1, 1. So all these 4 inputs can change. All these 4 inputs can change. So what this basically means is that in the Carnot map, you see in the SiC case, the transition was only between adjacent. So only one bit changes. So it will be only, there will be transition only to adjacent cells. But in this MIC scenario, if you look at these arrows, there may be longer range transitions because there are multiple bits involved. There are multiple bits involved. It's not a vertical or a horizontal change. It can be it can be vertical, but it is a longer range transition that can happen. And but one constraint we still have is that even if multiple bit changes, the change has to be monotonic for every individual bit. That means for every input, they may the entire bit w, x, y, z, all the variables may transition to a new value, but each of the variables w, x, and y, z in this process can change from 0, 0, 0 to, let's say, 1, 1, 1, 1, can change only once. Can change only once. Okay, so that means a monotonic. It's a monotonic change. Each variable can change it can change only once. Okay. So now for every, so this is a MIC transition, these arrows that we show here. For every such transition, we consider another set of minterms, which we call as the transition cube. It means that if we take the starting minterm and the ending minterm, and I look at all possible paths by which it can go. So from here to here, it means initially it was 1 0 1 0 1 0 1 0, and it ended up at 1 1 1 1. So that can happen in two ways. First is 1 0 1 0 becomes 1 0 1 1, then 1 0 1 1 becomes 1 1 1 1. Similarly, it can be a second way. 1 0 1 0 becomes 1 1 1 0, and 1 1 1 0 becomes 1 1 1 1. So there are two possible paths. But the criteria is that this path has to be monotonic, in the sense that in the sequence of the path, even though there are two changes from input to from source to destination, but in the process of this transition, every bit can change only once. That is, they are monotonic. So a collection of all such paths, collection of all such minterms which fall in these all these possible paths, would be called a transition cube. This we have already studied before. So there is a very easy to find it. What you need to do is that basically by visual inspection is even more easy. From the starting and the ending, you find out which of the bits are constant, they do not change, and then form a logic expression for those bits and get the corresponding cube. For example, here you see W doesn't change, and Y doesn't change. So WY is the constant part. So this cube covering these four things here would be called a so basically the WY cube, which corresponds to enclosing this 4 1, would be called a transition cube. Okay, also you have seen the formula, it's easy to do that. So you OR every bit and the output of all this OR. So if you have a MIC, every bit starting and ending you OR, and if there are n bits, you have n such product terms, and the resulting expression you get will correspond to the cube, which is the transition cube. And visually it means that it encloses all this. In this case, it's okay. It's only these 4, but if you consider wraparound and cyclicity for longer thing, there will be larger cubes. Okay. So now these transition cubes, if we look at these transition cubes for all the transitions, if it happens that in a transition, so look at all these paths. Okay, by the way, this transition would be static if the starting and end is same. So 1 static or 0 static. It would be dynamic if the start and end are complements. So 1 and 0 or 0 or 1. Those are, then we would call it dynamic. So this is this 1 means this is the output value, the expression value, the output of the function value. That is 1 here and 1 here. So this is static. And this is static 1 actually. Okay, so this is also a static 1 because it's 1 in the start and 1 in the beginning, this dashed line. But you see, if you look at the possible transition paths in the transition cube, so this is one possible transition path, this is one transition. In this transition path, this going to the top, then going to the left, this transition path, there is a 0. All these blank boxes are zeros. So there is a 0. Okay, so the function changes value twice, 1 0 and then 0 1. It's a non-monotonic change. The output function changes the value. So if there is such a non-monotonic change, then there is a function hazard corresponding to this transition. This function hazards, whatever circuit realization you have, they cannot be removed. Because what you will do, you will, in order to remove this hazard, basically, like we did in SIC, we'll use an additional product term and get, which will cover these 4 elements of the transition cube. But actually, you cannot have an AND gate because there is a 0 sitting here, so you cannot cover it by an AND gate. So you cannot remove it, whatever way you try. So these are unavoidable. These are intrinsic to the function. These are function items. But in the other case, you see this solid line, solid arrow, that is a logic hazard. So you can have realizations which will avoid these logic hazards. And why these logic hazards happen, it's easy to see, because if you look at this logic hazard, and okay, let us come to that a little bit later. So by the way, so there are three things that are involved here. One is this function specified by the Carnot map, all the positive min terms, on min terms, 1, 1, 1, 1, these are the function. And then there is a realization. This is a realization. And this realization corresponds to some grouping of these ones. So this is a grouping, this is a grouping. These cubes that I have drawn, this is a grouping. Okay, so this grouping corresponds to the bottommost grouping, let's say, corresponds to W and Z prime. W and Z prime. So this is the AND gate corresponding to that. This is the AND gate corresponding to the bottommost grouping. So every group that I have drawn here corresponds to an AND gate. There's the standard logic realization that we studied previously. So this, whether this hazard will be there or not, depends on how do we group these ones. Depends on how we group this one, equivalently how we realize the circuit. Okay, so every grouping corresponds to a realization. There will be some realization which will avoid these logic hazards. What is the realization? The realization is something adding an additional AND gate which will cover this transition cube for a transition. Will cover this transition cube. Note that in SIC what we did, transition cube was just two adjacent cells. So we had a AND gate covering two adjacent cells. Here they are larger. So we have a AND gate covering this transition cube. And others, why do we have a which do not cover this? Why do we have a hazard there? Because see, each of these AND gates will have their delay. Some will have less delay, some will have more delay. And in some unfavorable combination of the delays, hello, CRM? ও এগুলো হয়ে গেছে আচ্ছা ওকে ওয়েট I'm forwarding, wait. Okay, so what CRM told us that this is all covered. All right, so we want to do that. So let's go to a two-level hazard-free logic minimization. So our goal is the following: we'll be given a Carnot map like this. We'll be given some transitions. We have to come up with a realization. We have to come up with a grouping which will avoid these logic hazards. Function hazards cannot be avoided. Okay, for that, let us first come to some, just for recapitulation, let us come to some definitions. The required cube for a one-to-one input transition is you have to cover it. Okay, so the entire transition cube is a required cube. For 1 to 0 transition, it's a maximal subset of the transition cube. Okay, and then this is hazard free. You have to realize the privileged cube is, this is what is important. So if you have a dynamic transition, then the transition cube is called a privileged cube. Okay, it's a privileged cube. So let me come to the example later, and then we'll see that if, so let's say this is a privileged cube, and this is one of the realization cube, which is one of the AND gate. Some of the realization cubes are illegal in the sense that they intersect with the privileged cube, but they do not include the starting min term. That would be called a illegal intersection. A cube C, any cube C which you are having a realization not containing the starting min term, has an illegal intersection with a privileged cube. And we should not have any cube in your final realization which involves an illegal intersection. Okay, so suppose there is we have to take care of a so these are the condition for a hazard-free transition, logic hazard-free. Function hazard we are assuming is not there. So if there is a 0-0 transition, then there is the realization is C is an realization. C is some. So this is an example realization. This is an example realization. This collection of these cubes. Okay, so if C is free of logic hazards for the input changing monotonically from M1 to M2. Okay, if there is a 0-0 transition. 1-1 transition, if M1, M2 is included, then it is a, so both these statics are taken care of this way. If you have a dynamic, we'll talk about 0-1 transition later, then the privileged cube, any realization C, and if it can be there in the realization if it is free of any illegal intersection with the privileged cube M1, M2. Okay, so these are the requirements. These are the requirements for a hazard-free MIC realization given a transition. So that we can have an equivalent goal. You have to implement a two-level circuit where each required cube is completely contained in some product. No privileged cube is illegally intersected by a product that is there in the realization. So these two goals should be satisfied. So let us take an all right. So so to do this, what we do is that, so this is the requirement. So what we do, you remember your Quine-McCluskey method or the Karnaugh map based realization. What we do to have a kind of minimal realization, we identified all the prime implicants, the essential prime implicants and others. Then using the chart of Quine-McCluskey or just by Karnaugh map, we find out the prime implicants, the list set of prime implicants which cover all the minterms or positive minterms. Or maybe they don't care if they are there. But here we constrain this a little bit further. We say that all the prime implicants are not at our disposal to cover the Karnaugh map. Only some prime implicants which satisfy some property called DHF, dynamic hazard free, only these can be used to cover. Okay. So instead of prime implicants, DHF prime implicants are identified. So first step, two-step process. First step, you identify all the DHF prime implicants. Second step, use this DHF prime implicant to cover all the required cube. Okay, cover all the, and of course all the ones also. So if you can do these two, you basically get a hazard-free realization. Okay, so these, as we have said, are the steps. Generate all DHF prime implicants. So this has three sub-steps. Generate all the prime implicants, forget about the hazards. Maybe shrink them so that they satisfy the DHF property. The DHF property is just this absence of illegal intersection. That's the DHF property. That's what is required. Reduce, some of the prime implicants will not satisfy that. So shrink them so that they satisfy and make them DHF. Any of these reduced implicants, if they are covered by some other implicant for minimality, remove them. Identify all the required cubes. Okay, note that the on min terms are always covered by the required cube. So this will see that on min terms will always be covered by the required cube. Okay, so and you from the transition cubes you can find out what the required cubes is. Then once, so these are the set which you can use. These are the cubes you need to cover. Solve the covering problem. It may turn out that this may not be satisfiable. You may not have a solution always. You may not be able to cover them using only the DHF prime. You cannot have a hazard-free implementation. Let's take as this example. So see, this is typically what you will be given in this design talks is that you will be given some function which you have to realize. You can be given an expression. We have written it down as a Karnaugh map, and then you will be given some transitions, some MIC or SIC. Here there are MIC transitions that are possible in the circuit. What you have to do is that given these functions as well as the transitions, you have to make a minimal hazard-free realization of this function. So basically, how do you do that? You basically, just like a normal realization, you find out covering cubes, and for each covering cube have an AND gate, connect up all the AND gates by a OR gate in a two-level implementation. Okay, so let's do that. So this is a function, and I have four transitions. Note that each of these transitions are function hazard free. They do not have a function hazard. Okay, they do not have a function hazard. So this is what is given. So what we will do, each of these transitions will take care of. We'll take care of each of these transitions, find out what their DHF are, and find the set of available DHF, use that to cover this kernel map. Okay, so let's see what are the required cubes. Look at this first transition. Note that this is a dynamic 1-0 transition. This is a dynamic 1-0 transition, but note that it is function hazard free. This function hazard free. Okay, this is a dynamic 1-0 transition. What are the required cubes that you need to cover? This one. This transition is a required cube you need to cover, and this transition is also a required cube you need to cover. Okay, so they correspond to A prime, C prime, D prime, and you can check out easily from the kernel map A prime, B, C prime. So these two cubes you need to cover. These are the required cube for this transition. Similarly, the required cube for this transition, you can see that note that here I am not covering the both, because this is 1-0, 1-0. This is not to be covered. These 1-1s are to be covered. Here there are 1-1, 1-1, 1-1, 1-1. Both paths have this. So the required cube here will be this entire transition cube. Is this the transition cube? Yeah, will be the entire transition cube. So it is AC prime. This is the required cube. Similarly, let us look. This is a larger transition. Longer range transition. This is a 1-0 transition. Okay, but you see the transition cube includes this also, because there are these following paths. You can go like this, and then you can go like this. You can similarly go like this. You can go like this, and then you can go like this. Okay, so these are also included in the required transition cube. So this is the transition cube. And what are the required cube? Required cube is, you see, this is one transition that needs to be covered. This is one transition. So these required cubes are nothing but you need to cover them to avoid glitches. You need to cover them to avoid glitches. This is the BCD required cube. This is another required cube. You need to cover this as well as this, as well as this, as well as this. So this is a required cube. A prime C. This will come out to be. This is another required cube. So these two required cubes you need to cover. So whenever we make our groupings for the realization, we have to cover. So these two I have to cover. Sorry, these two I have to cover. Then this I have to cover. Then this I have to cover. This I have to cover. So these four green boxes, four required cubes I need to cover. By the way, one thing you can visualize that if you take a intersection of the required cubes, you are covering all the ones. Sorry, if you take a union of the required, you look at this required cube, and this required cube. You take their union, you will see that you have covered all the one elements. Okay, so now let us, so we have two dynamic transitions. This one 1-0 and the bottom one 1-0. We have two dynamic transitions. The required cubes for this these privileged cubes, these are these transition cubes for this privilege for this dynamic transitions. We call them as privileged cubes. So these are the privileged cubes. There are two dynamic transitions, so there are two privileged cubes. This is a privileged cube. This is a privileged cube. So now you see we have two kind of categories. One is a required cube, and now we have some two privileged cubes. And these shaded ones are the starting points of these privileged cubes, Now, the thing is that no realization, any cube that you have in your realization can intersect any of these privileged cubes unless that cube also includes these shaded boxes, that's starting points. Otherwise, it is illegal. And you should either modify it or you should remove it. Okay. So now let us look at from this original Carnot map, what are the prime implicants that are there? Let us do them. So we actually have 7 prime implicants. I'll show all of them. So this is the first prime implicant shown in blue. This blue dot dashed line is the first prime implicant. Okay. It's not illegal. That's why I've written a tick, because it intersects with this privileged cube. It intersects with this privileged cube, but it also includes the starting point. All right, so this is a valid. This prime implicant is the prime implicant AB. If we look at this, it is AB. This is valid. No, I think I have made a mistake. This will not be AB. This will be C prime D prime. Sorry, I did not edit this. This is C prime D prime. Oh, sorry. It's written here. Sorry, that's something. Sorry. This is C prime D prime. Yes. This is another prime implicant, A prime B. This is also not illegal. It intersects with this privileged cube as well as this privileged cube. Okay, this privileged cube but it includes the starting point also. Similarly, this is also a valid prime legal prime implicant because it includes this. This is also a legal prime implicant because it does not intersect with any of the privileged cubes. Privileged cube, mind you, are transition cubes for dynamic transitions. This is another prime implicant, A prime C. This also is legal. It contains this. Now let us look at this prime implicant. It intersects with both, but it does not contain the starting point of this privileged cube. It does not contain the starting point. So with respect to this privileged cube, this is illegal. This is illegal. Similarly, this prime implicant, this also has an intersection, but this does not contain with both of this privileged cube, but does not contain this starting point. This is also illegal. So what we will do is that we will edit this prime implicant and this prime implicant. Note that all these previous prime implicants that we had, this P1, P2, P3, P4, they are DHF. They are already DHF. They are hazard free. But these two are not hazard free. So what we will do is that we will change them so that they are hazard free. So this is one not hazard free. This is an illegal intersection is there. So what I do is that I break this prime implicant reduce this into these two prime implicants to avoid this intersection. To avoid this intersection, I reduce it to these two. But this is also still illegal because this intersects with this and does not contain this one. So I break it down further. Okay. So what I do is that I remove this. I remove this BCD. Yeah, I remove this BCD. Yes, I remove this BCD is this one. This one I remove. I get this. I get this because this was intersecting and it doesn't contain. So wait a minute. Just wait a minute. I break it down into this. Okay. Then what happens? Then this is intersecting with this, but this contains this. Okay, let us look at this. So we retain this, and then let us look at this, the other one. Okay, here also the problem is this intersects with this but does not contain the starting point, so I have to reduce it further. Okay, so this I retain, this doesn't have a problem. Sorry, yeah, it's correct. So I break it down into this and this. This is legal, this is legal, this BCD thing is legal. So now this is a DHF, this is one of the DHF. Look at the other one, this is still illegal. This is still illegal among these two, this is still illegal. So I have to reduce it further. I reduce it to this. All right. So this prime implicant kinds of get reduced to this and this. This and this. Okay. So all right. So now we say that what you have to do is you have to remove the redundant one. So if there is a prime implicant which we have, which is already covered by another prime implicant, we have to remove it. So let's see, is there any prime implicant already covered? So this is already covered by this prime implicant. This prime implicant covers this. So this prime implicant is not necessary. I don't include this. Okay, but this is not covered. This is not covered by this. So this is there. Similarly, look at the P7. P7 was this prime implicant, this and this. Let us see what is there. So this and this is the P7, seventh prime implicant. This has an intersection but doesn't contain the starting point, so I have to discard this. I am remaining with only this. This is legal because it contains the starting point with this intersection. All right, but this is redundant because this is part of this prime implicant. This part of this prime implicant is redundant. Okay, so I discard it. So I am left with only the following. I am left with AC prime. So okay, but let's look at this. So I am left with A prime C. I'm left with C prime D prime, A prime B, BC prime, AC prime. These prime implicants are DHF. They do not have any illegal transactions, so they are DHF. We can have them to cover. This is also there, A prime C. This was not legal, so we reduced it by breaking it down. This was also not legal, we reduced it by breaking it down, and after breaking down we checked that it is redundant or not, it is covered by something else or not. If it is not covered, we have it. So that way I think we have this BCD, and this one is already covered, redundant. So we have AC prime, BCD. BCD was, these two were anyway prime implicants and hazard free. So they were DHF. This was originally containing hazard, but we reduced it and left with this much after removing the redundant part. So these are the prime DHFs. These are the DHFs implicants left with us. And these are the these are the prime implicants that we need to cover, DHF prime implicants that we need to cover, and so this is the covering given. This is the covering given. Okay, so this covers both P2, P3, and so on. Okay. So see, just like this method of Quinn-McCluskey, so we have a set of prime implicants which we need to cover, and then so this covers this covers this. Then we usually follow the same procedure. We look for essential prime implicants, and then retain them and see what is covered by them. Drop them from this chart, and then have then solve the optimization problem to have the minimum. So the same process you follow here. And if you do this, you get the following realization. So if you have P2 and the rest, you will have this realization, and if you take P3, you have this realization. Okay, so these are the two possible realization in the sum of product form, and all these two are hazard free. Now what may happen is that this may not, if the hazards were not there, maybe we could have had a smaller circuit. But to avoid hazard, some amount of redundancy is required, additional gates will be required. So it's kind of suboptimal. So it trade off optimality in terms of number of gates with hazard freeness. So this is the process. So typically as a design process, what you have to do is that this will be your starting point. It will be your starting point. You will be given this, you will be given a function, maybe as a Carnot map, maybe as an expression, and then you will be given some transitions, and then you have to go through all this process, identifying required cubes which you need to cover, identifying privileged cubes and their starting points, identifying DHF prime implicants if they are not DHF by looking at illegal intersections. If they are not DHF, convert them to DHF by reduction and removing redundancy. After that, we will end up with a set of DHF implicants, and then you try to cover all the prime implicants using these DHF implicants. Okay, same following Quinn-McCluskey or Carnot map, and you end up with a realization, whatever realization. So your realization will be in terms of this DHF. So each of the term here you will see is an DHF. Each of the term here will be a DHF. And thus they will be hazard free. All right, so that's it. That's it. I think that's all I had to say. This covers your hazard free circuit design problem. And now I think if you have any question, that's fine. Otherwise, we will move to other topics.